Hello and welcome back to the Programming Bootcamp. My name is Gabor Szabo and hi Nora.
Hi.
Finally, we arrived to something that's going to be probably interesting to you. We are finally going to discuss a lot more about scientific programming or programming and scientific related programming. So let me share the screen and show you the slides. And actually, in this video, I'm going to show you a general overview about the scientific programming, a little bit about chemistry, a little bit about biology, and it's embarrassingly too small. And my hope is that after the course, you'll get into much deeper in this, and then you're going to explain to me and give me all kind of other ideas and examples, and then we can enhance the video and create maybe a new recording of all the additional things that you encountered, okay? So this is just a regular slide. In the slide series, we search for SciPy, okay? And we are going to cover these three chapters here, the SciPy, the biology, and the chemistry one. So first of all, SciPy is what they call an ecosystem of scientific related libraries in Python, okay? Tons of them, various things, okay? So this is just a little overview about all kind of modules, and then we'll get into some of the specifics ones. BioPython is, I'll just visit the website so you can see. The BioPython is a library with all kind of biology related tools. Okay, all kind of modules specific for biology. NumPy, I mentioned earlier, is the library that allows us to create vectors and matrices, and they can handle computation on these very fast. Okay, if people who are coming from a background using Matlab, for example, they are really used to this kind of thing, and they're sort of we're missing up till now. Okay, so how can you do all these things in Python? So that's the NumPy library provides these features. Pandas is another library that uses behind the scenes NumPy and provides you with what they call data frames. Basically, think about just like CSV files, handling CSV files. So basically, a matrix of data that has titles. In general, that's more or less that's what it is, and can do all kind of very interesting things with it. Matplotlib is one of the low-level. Okay, I have already too many windows here open, but it's a relatively low-level plotting library to create various graphs. Okay, and I am personally really bad at creating graphs. Okay, Seaborn is a library that uses Matplotlib behind the scene to create nicer graphs or make it easier for you to create graphs and so on. Okay. Bokeh is another visualization tool. Okay. So Seaborn is actually from the West Wing. I don't know if you have seen, I think that's the series. It's a person there. Okay. And that's the reason they called it the library. So some of these libraries have really fun names. So Bokeh is also some visualization tool. SciKit-Learn is a machine learning library in Python. The name comes from SciPy toolkit. So it can do machine learning, various stuffs. Okay. Each one of them can, I guess, to learn each one of these is a couple of days of learning. Okay, so just TensorFlow is another machine learning framework that was created by Google. Okay, let me just visit the site. So we have these nice views on. Can't see much here. Yeah. Okay, so they have a nice website. Keras is a deep learning library using TensorFlow behind the scene. So it's all built one on another, okay? Orange,
just a second. What does deep learning mean?
wow. Whoa, I don't know. I can't really explain it really well, but in general, it's using neural networks to create basically a self-learning system. So okay, up till now, and many of these libraries still assume that you know what you're doing, okay, and then that you have some assumption and you would like to do some computation one after the other. There's a whole set of area where sort of we say, okay, we have a bunch of data. We don't really know what is the relation between this data, and let's have this. Let's use this system, okay, whatever we call it, the system, and let's give it the data. Let's give it the data and hope that it will be able to come up with the connections. So if you have like 2 input variables and then 1 output, then it's relatively easy to figure out what is the function generating, or what is the relation between them. If you have 10, it's getting difficult. If you have 100 different input variables, then it's getting probably impossible to come up with the idea. And yeah, we had this whole discussion about this also in the family, that people coming from the, let's say, old school research side, where you have some assumption and that you are trying to prove it. Okay, create data and then try to prove it. And then some other people coming with these new ideas, okay, saying that, okay, we have a bunch of data, we have no idea what to do, and we just throw it in the computer, it will come up with some result, and then we're going to explain it. Okay, and I guess somewhere there is some middle ground at the end. So it's not, I'm trying to point out these extreme years. Okay, so deep learning, the way I can explain is that it uses a deep structure of this neuron. So a neural network is a deep structure, so many levels, and then each neuron is basically is trying to simulate what neurons in the head work, or what we understand, or what we can implement, or what. So it basically really simple things, or simple devices, but you have a lot of them. And then the combination of them creates some kind of thing that can learn. And they call it deep because I think that the reason deep is because it's not because of a deep thought and that kind, but just many levels of this. Okay.
Right, thank you.
I hope I didn't just totally said something incorrect, because that's not really my area of knowledge. Okay. If anything, my son knows a lot more about it. Okay, so you go ahead and ask him. Okay, Orange is slightly unrelated to this. It's a tool itself. So all of these were, I think, libraries that you can use in your programming. Orange is itself a tool that, like an editor, okay, that you can use to program. Okay, and I don't know if how useful is that, but I thought that I mentioned it here. Okay, so it's not really directly related to our system or way of learning, because we are trying to build programs. Airflow and Luigi are 2 systems that sort of trying to solve the same problem. The problem is that you have many operations that you want to do on your data, one after the other, and you somehow would like to manage these operations. That some operations, maybe you need to spread out to many computers, or you can spread out to many computers because you can do them parallel. Some operations you can do only linear because you all need the whole data together. Sometimes you might be able to do, once you did some of the steps, you can stop and then go on later on. And someone has to be able to handle this. So maybe you have 7 steps and steps 4 breaks down, or you figure out that you can improve it. And then instead of running the whole thing again, you would like just to run from step 4 and on. And of course, all of this you can manage manually, but there are these tools that can help you manage these workflows or data pipelines. These are the works. And as you can see, some of these are coming from well-known companies that they needed for their own data analysis things. And then at one point they decided that they release it as an open source project, and now everyone can use them. Okay. This is just a link to an article, a blog post I wrote on how to use the GPU, and I'll explain it in a second, to improve computation. Okay, so in the computer you have the main processing unit, which is called the CPU, or central processing unit. That's very good at handling all kind of stuff, giving instructions to your computer, managing your computer, your screen, your keyboard, your printer, your microphone, everything, but it's not that good in computation. Okay, it can do computation quite well, but that was not the original design of it. There is something else which is called the GPU, or graphical processing unit, that originally was created as a simple and stupid processor that can do nothing, just drawing on the screen. Okay, that was sort of the idea, because the CPU was too expensive, and they decided, okay, we just give something cheap just to handle the part that the screen needs. That was, I don't know, 20, 30 years ago. And then a couple of years ago, they found out that there is all this data science thing that needs a lot of computation. And then they found out, okay, we have this GPU that up till now was sort of on the side. It wasn't that used much. And this can do way better computations, multiplying matrices and whatever. So matrix level computations or many dimensions computations much faster than the CPU can do. Okay, and the reason the GPU can do it much faster, bless you, is because it can do it in parallel on the level of the hardware. Okay, so it was designed for that. They didn't think back then apparently that it's going to be that useful. So these days, GPUs are way more expensive than CPUs, and they create a lot more heat also. So most computers, most a little bit higher-end computers have some GPU in them, but they are usually low in order to handle the screen. But they are usually relatively low-level GPUs. Okay, but you can buy for thousands or tens of thousands of dollars really, really powerful GPUs that can make your computation much faster. Okay, but they need, so you need to transfer your data to the GPU. Okay, or your program transfers the data to the GPU. So if you have relatively a lot of data and your computation is relatively simple, then still using the CPU is better than the cost of transferring the data and having the speed of the GPU, because the data transfer cost is high. So I found the GPU at home. Okay, long story. And it wasn't very powerful. It was quite old. It was an NVIDIA Quadro 2000. So these days it would be unusably slow. And then I tried to figure out when can I make it fast? Because the first example I had, it has so little computation that my CPU actually ran faster. But in this article, you can see a little bit more about the information on when it gets faster than using the CPU instead. So it's not, I mean, for now, for basic programming, this is not really relevant. But when you start reaching the point that you have a lot of computation and for your feeling, it gets starting to be slow, okay? because it takes more time than, let's say, you prepare your next tea, okay, or whatever. Then you'll start thinking about, okay, how can you improve it? And then this whole discussion might be relevant, and start thinking about, okay, maybe I'll need to invest in a GPU, or think how can I speed up my computation, okay? And if we are already here, let me just talk a little bit about something else. I don't remember if I mentioned it. So you would probably write on your own computer. You have some relatively cheap computer that has a very limited processing power, limited to our needs, or it's really powerful for the daily work that you do. But if you start doing a lot of computation, it's going to be, at one point you'll feel that it's not powerful enough. You don't have enough memory to hold all the data maybe, or the CPU is not fast enough, or whatnot. And then you can, in scientific institutions, sometimes you have your internal, what we call a cluster. That's basically many computers, and then you might be able to use that. And if you can't do that, okay, then you can use what we call the cloud, which is basically various companies, primarily Amazon, the Google, the Microsoft, but there are also smaller ones, providing you with a bunch of computers that you can rent by the minute, I think. And then some of these computers can have, I don't know, 1,000 CPUs at the same time, and a terabyte of memory. So things that you probably won't even have in disk space usually in a normal computer, but you can rent it for by the minute from these companies. And of course, once they get big, they also start costing a lot of money. But if you have some very special computation, then that's another way to rent basically a computer, put the data there, put your code there, do the computation, and then shut down the system. So you might run it for a couple of minutes, a couple of hours, okay? But that's another way, instead of buying your own hardware, because buying a powerful system is really expensive. So renting for a short time can be much cheaper, okay? Of course, if you need it for a long time, that's gonna cost. Okay. And Octave, which is unrelated actually to Python, is just another system for, which is like a Matlab. It's an open source tool that's tries to be a replacement for Matlab. Okay. And why I mention here Matlab many times, because many people, especially from scientific background, use Matlab. And the huge drawback of Matlab is that, well, at least outside of the academic world, it costs a lot of money. Okay, then that's one of the problems with Matlab, while all the Python libraries are open source and free. Okay, and you also have various technical limitations, of course, in Matlab, and you are dependent on the company providing Matlab. I mean, the Matlab company providing the tools. So if you find a bug or you need a new feature, you're dependent on them. While if you're using open source, whether it's Python or something else, whatever you open source, you can write your own if you would like, okay? And most likely some other people also, or at least you can cooperate with these other people, okay? Okay, way too much about this, but okay. And then there's a bunch of links here that are primarily, I think I uploaded just for myself to find all kind of extra information. So we won't visit these. These are just various, I don't know, papers and so on. Okay, so that's about the generic notion about scientific Python. Okay, the other thing, I think maybe that we can take a break now, okay? And then in a separate video, we're going to record this, okay? What do you think about it? Okay, so let's do this.
Sounds good.
Okay, and then we'll have a separate video for the biology and for the chemistry part. Okay, so see you for now. Bye bye.
See you.